come in, your exam will have two parts to it. You'll have a multiple choice part. That multiple choice will be a non-calculator part. You'll have a free response part. That free response part will be a calculator-based part. Let's see. That's kind of it. Students tend to do well on the exam, so there's that. That's a little bit.
People usually do well on actually exams.
Yes. So, yes, they do. Typically, my students have a better than 80% pass rate on the AP exam. I've had years where I've had all 45s. Last year was a weird, bad year for me. It was actually my worst year. I think snow days were a large factor.
Like how, like what do you mean, like not a lot of people passed?
No, it was 65% pass, which is not good.
But you always have at least a 65% pass.
That's the lowest I've ever had, yeah. Every other year except that one, I think was 80% higher. How many? Oh, how many problems are there? 20 multiple choice questions and 3 free response questions.
So read or
Like that's it?
Well, those are parts.
It's like part A, part B.
questions are like 3 questions.
You're going to have one period.
Yeah.
Yep.
Oh,
And the actual AP is 45 in an hour and a half and 6 in an hour and a half. You will be well prepared because you'll find that the questions on the AP exam are similar to the ones that I give. And you will also find that we've done a lot of practice problems.
Without even knowing.
Or with knowing it. The entire month of April was blocked off for AP practice.
What is
All of them.
May 7th, I believe.
we do have the
We actually do a little bit of competition survey. And then you graduate.
What are we doing Friday?
This week. So we're actually going to do a surprise activity. All right, that takes care of those questions. We have at least 2 things that people want to cover. I also want to do a quick overview of derivatives.
I know I've asked you this before, but in the past, about a month ago, can you go over the one with the, I can't remember what it's called, but it's the trial and error one. Like, say if you get an answer for these 2, it has to be between these 2, and then once you get an answer, and you like work, you get like estimate, and through your estimation, you find
Oh, like a bisection method?
Yeah, there was that.
Won't show up on the exam.
Okay.
Wait, are you talking about the thing where on the calculator you have 2 points and it finds the one exactly in the middle?
Yeah.
That one?
Yeah. Okay. All right, so let's do an overview of derivatives. Derivatives were one of our big uses of limits because the derivative of a function at point C is the limit as x goes to C of the difference quotient f of x minus f of c all over x minus c. Or if I wish to compute it at point x, I take the limit as h goes to 0 of f of x plus h minus f of x, and all of that divided by h. This limit definition was at first the only way that we had to compute derivatives, but we didn't like it too much because it was complicated, especially if my function involves, say, a large polynomial or something like that. And so we quickly developed a set of derivative rules that helped us find the derivatives of all of our elementary functions. And those derivative rules include things like the sum rule, the difference rule, the constant multiple rule, product, quotient rule, and chain rule. We had derivative rules for all our trig functions, for the exponential functions, the logarithmic functions. And so you'll want to review all of those for sure. One of the more obscure derivative rules that we had was the inverse function theorem, the derivative of the inverse of f. And so I'll talk about that at this time. If I wanted to compute the derivative of the inverse of f, then I started with the fact that f and f inverse are canceling functions. They cancel each other out to give x back. And we use that fact to solve the equations. And so if I now take the derivative with respect to x on both sides, then the derivative on the right-hand side is 1. The derivative on the left is given by chain rule, so that f inverse prime is 1 over all of this, f prime of f inverse of x. So that's my form for the inverse function theorem. But then the question was, how do I actually use that form? So a typical kind of setup might be something like this. Suppose I have a function f, and I know some things about f and its derivative at different points. Hello, okay, and let's say that the derivative then is going. Should my derivative be negative or positive? Probably, if f has this pattern negative. Negative, it should be going downwards, right? So let's say f prime is negative 1, let's say it's negative 2, let's say here it's negative 4, and here it's negative 3. So I have some information about f, but I don't know what the equation for f is. Okay? And now I ask the question, what is f inverse prime, the derivative of the inverse of f at 2? And so to think through that carefully, I start with my form. I would say that using the theorem, f inverse prime of 2 should be the same as 1 over f prime of f inverse of 2.
How?
Because that's the inverse function theorem.
I thought the inverse function theorem was just the inverse, or no?
The inverse function theorem, what the inverse function theorem does is it gives me the derivative of f inverse even if I don't know what f inverse is.
Okay.
Yep. So having set that form up, now it's just a matter of evaluating by working inside out. To find f inverse of 2, I go to the place where f is 2, and I find the x that corresponds to it, which is x equals 1. And having found the x that corresponds to it, I am now going to find the f prime that corresponds to x equals 1, which is negative 2. And there we are, and we're done. So finding values for f inverse is a matter of reverse lookup. If I want a value for f inverse, then I simply go to that corresponding f value and look up, reverse look up the x. So f inverse of 3 would be 0. F inverse of 0 would be 2. F inverse of negative 2 would be 3. F inverse of 5, we don't know, because there is no corresponding value here. How about f inverse of 1? We also don't know, because there is no corresponding value here. Does that make sense to everybody? Is that better? Good. Most derivatives of inverses can also be thought of in terms of implicit differentiation. So for example, when I wanted the derivative of the inverse sine of x, remember these inverse function derivative rules, inverse trig function derivative rules? Then the way that I got that was to use some implicit differentiation. My problem is that I have y equals inverse sine, and what I want is to find dy dx. And since I didn't have a rule for this, I said, let me cancel out the inverse sign by taking the sine of both sides. And when I take the sine of both sides, then the function and its inverse cancel, giving me x back, because that's what inverses are. And now I take a derivative with respect to x on both sides. And on the right-hand side, I get 1. On the left-hand side, I get the derivative of sine y with respect to x should be what?
Cos y times y prime.
Yes, cosine y times dy dx. And notice that these two come out from chain rule, right? They also correspond to, in our proof of the inverse function theorem, here is my f prime of f inverse, and here is my f inverse prime. And now when I solve for dy dx, I get 1 over cosine y, a perfectly good answer, but it is implicit. So if I want to write my result explicitly, I need to find out what the cosine of y is. And so I go back to the fact that x equals sine y. And if x is equal to sine y, then cosine y will be the square root of 1 minus sine squared y from the Pythagorean theorem, Pythagorean identity, which is the same as square root of 1 minus x squared. And so that allowed me to replace in my form right over here to get the derivative of the inverse sine. And you remember that was one of our 3 inverse tree function derivatives. Yes?
Can you do the same thing with inverse f of x? For example, like if it is in the tree code?
Yeah. We did it with exponentials to get the derivatives of logs. Is that better? Okay. Let's see. What else about computing derivatives? That was computing derivatives using derivative rules. In addition to computing with derivative rules, we could also compute it. How? What else? How else can I get the value of f prime? With a calculator. What's the magic button for that?
7.
Second calc.
Second calc dy dx. That's right.
Oh.
Yeah.
You're just randomly saying.
You thought she was being a smart one.
No. I think it's 7 point.
Whichever one, it's second calc dy dx, that's right. And also in derivative. Will get us his values high.
Maybe the 4th one, actually.
Okay.
No, it's 6.
Can she come a little later?
Yeah.
Possible? Okay.
It's 6, by the way.
It's the one that says dy dx.
Yes.
So now we know when they say, how do you work out f prime? You say 6.
How else could we compute derivatives? Well, sometimes we were given tables of data, right? So I might be given a table with some x values and some f of x values. And I might ask something like, what is f prime of 0.2? And here, I cannot use second calc dy dx because I don't have an equation to graph, and I can't use any derivative rules. So I'm going to have to estimate the limit by computing the difference quotient for as small an interval as possible. So I'm going to write f prime bracketing 0.2 as approximately f of 0.3 minus f of 0.1 over 0.3 minus 0.1, which is equal to 7 minus 6 over 0.2, which is equal to 5. And so here, what we're doing is we're computing, what do we call this when we take the change in f over the change in x? What is another name for that, schools?
Average.
Slope or average rate of change, that's right. It's an average rate of change over the smallest time interval I can possibly choose to get an estimate for the instantaneous rate of change. There was a hand somewhere. Yes, you got it. Okay. What if I wanted f prime of 0? Well, f prime of 0 can't be done by bracketing because there's nothing over here. So I would simply bracket to the one side where possible and say that's approximately f of 0.1 minus f of 0 over 0.1 minus 0, which would be 6 minus 5 over 0.1, which is 10. Does that help? If I were to be specific about it, this is not really a good estimate for the derivative so much as it is a good estimate for the derivative from the, which direction? From the right, because I'm only going to the right for my estimate here. So I could also write this as f prime plus of 0, because I'm estimating only from the right-hand side. And at the endpoint, that's the best we can do to estimate our derivative. So we have these different ways of finding derivatives. We can do second calc dy dx. We can use our derivative rules. We can do a difference quotient or average rate of change estimate. What if I'm just given a graph purely? How would I find the derivative at a point? Draw a tangent line and then find its slope. All these different ways of computing derivatives. Now that we have them, what can we do with them?
You can create line equations.
You can what?
Create line equations.
Yes.
Show them off to your friends.
What's that?
Show them off to your friends.
Show them off to your friends. That's right. Did you know that if f of x equals e to the cosine x, f prime equals sine, negative sine x times e to the cosine x? Wow. Now I'll go out with you.
Lines. Calculus.
That's right. Okay. So using derivatives, we actually had several uses for derivatives. One of the most basic was to create a tangent line that approximates my curve. And here was our tangent line approximation. But please, please do not think of this as a special new formula. This is just point slope form. I have a line that goes through the point C, f of C.
Did you know something else we learned about this?
This is also called the local linear approximation. And it has a slope of f prime of C. Here's where a lot of students will screw up. So I want you to watch this carefully. Notice that my slope is not f prime of x. It is f prime of C, f prime at the point of tangent. So for example, if f of x equals, say, tangent x, and I want the tangent line, unintended, at x equals pi over 4, then my point will be pi over 4 comma tan of pi over 4. What is the tangent of pi over 4? 1. And my slope will be the derivative of tangent. What is the derivative of tangent?
Secant
Secant
squared.
squared evaluated at pi over 4. My slope is not secant squared x. It is secant squared of pi over 4 because that's where I'm drawing my tangent line. So I still have some students that are fuzzy on that. Please do not be one of those. And to find the secant, I would write that as 1 over cosine.
To find the secant line?
No, to find the secant of pi over 4.
Oh.
The trig function is secant of pi over 4, which would give me 2. So that now I have a point and I have a slope, and I can immediately write y minus y1 equals slope times x minus x1 for flex. We haven't done a lot with these tangent lines yet, but we will in the near future, as in January, use these to estimate values of functions and stuff like that. So the tangent lines are going to be useful very soon. We also had a related concept, which was the concept of a normal line. Do you remember that? And the concept is that the normal line is perpendicular to the tangent line. So if the slope of the tangent is dy dx at x equals c, then the slope of the normal line would be the slope needed to make it perpendicular, which is what?
Whatever F prime.
Not quite.
Negative.
Negative 1 over f prime. Negative 1 over dy dx. We didn't do a whole lot with normal lines, but we did do a couple of assignments on it. So that was our first use for derivatives, was drawing tangent lines and normal lines. And if you want a picture for it, you can draw yourself a curve right here. And if this is f of x, and I choose a point C for tangency, then my tangent line is going to look like this. Here, my normal line will be perpendicular to it. It is going to cut right through the curve and be perpendicular. Just like that. Okay. What else could we do with derivatives? Well, we actually had some useful theorems about derivatives. And Raleigh's theorem, right? Mean value theorem was one of the big ones. Fermat's theorem. Intermediate value was not, that was more of a continuity theorem related to limits. But the extreme value theorem. So we use derivatives to say something about the shapes of curves. And we're going to do a lot more of that in January as well. In particular, we said that if f prime is positive, then what do I know about, if f prime of c is positive, then what do I know about f at c?
Increasing.
It is increasing through c. That's right. And if f prime is negative, then f is decreasing through c. That's right. Okay. And that means that if f of c is a local max or min, what has to be true about x equals c? It cannot be.
It's ghost flight.
If f of c is a local max or min, then what cannot be true at x equals c? F cannot be increasing, and it can't be decreasing.
It's a critical point.
So therefore, it has x equals c has to be a critical point. And what does it mean to be a critical point?
It is 0 or doesn't exist. The derivative.
The derivative is 0 or the derivative does not exist. We call these the critical points of the first type, and these the critical points of the second type.
Can you explain that a little bit?
Absolutely. If I draw myself a curve that has a local max at x equals c, then my derivative can't be positive, because if it were, my curve would still be going up. And my derivative can't be negative, because if it were, my curve would still be going down. So instead, my derivative either has to be 0, horizontal tangent, or it has to fail to exist. Sharp point. Or cusp. Yes.
What if the does not exist is, like, say, goes off into infinity, like that type of discounting, then what would it be?
You mean that type of non-differentiability?
Yeah.
Then you would have a critical point, but that critical point would not be a local maximum.
So when,
So notice that not all critical points are local extrema. All extrema, all local extrema are critical points. So our slogan is local extrema only occur at critical points. Yes.
Can you explain the difference between, or how to, the difference between local maximums and universal maximums?
Absolutely. Yes, I sure can. All right. So this was our theorem. If f of c is a local max, then x equals c is a critical point. And the slogan for that was that local extrema only occur at critical points. If we now consider absolute maxes and mins, absolute maxes and mins can occur in two different places. And that was our critical point endpoint theorem. If f of c is an absolute max or min, on a closed interval a to b, then x equals c is either a critical point or it is an endpoint. It is either A or B. In other words, absolute maxes and mins can occur at two places, critical points or endpoints. Right.
So an endpoint can't be a local maximum
Correct.
because it has to be like
On an open interval. And the endpoint right there is
So
not in an open interval.
so when there's an open interval, there's no absolute maximum.
There might be, but they would have to be critical points. There would be no endpoints.
So if there was a critical point on an open interval, then it would be a local maximum.
Okay? So you're getting your logic kind of dorked up. Local extrema only occur at critical points.
Right.
It does not follow that critical points are always local extrema. They're not.
Right.
Right. Okay. Absolute extrema only occur at critical points or endpoints. And that led us to our method of finding absolute extrema, the critical point endpoint method. If I have a function and I need to find its absolute extrema, then I find the critical points, I identify the endpoints, and I evaluate the function at each one of those points. And the biggest one is the max, and the smallest one is the min. If my function is continuous on a closed interval a to b, it has an absolute max and min. That's the content of the extreme value theorem. Right? If it is continuous on an open interval, it may or may not have an absolute max or min. If it does, those will be at critical points. But if it doesn't, it doesn't.
But how do you know if it's an absolute min and a max min if you don't see the whole? If it's like not an open interval, like how do you don't see the whole?
Yeah. At this point, you have no way of knowing that. So you are hoping, and you will only be provided problems with finding absolute extrema on closed intervals.
Somewhere else would not provide it on open interval.
Correct.
So how would we find the local? So the local extrema would only be a critical point on a closed interval.
Local extremas will be critical points, period.
Okay, but so then it could be a local and absolute extreme.
Yes, that's right. There is no requirement that it be one or the other.
Okay,
But
I
it
get it.
can occur external, occurs at like entry points.
No, it's not. They can only occur at critical points because to be a local max, it has to be local on an open interval. And if I have an endpoint right here, like there, then there is no way to draw an open interval around it because I'm already at the endpoint. Yes.
Will the discontinuity in a function always be equal to this?
Yes. Because it is a place where we are not differentiable. Hey, speaking of, one of the things that we hadn't talked about yet is points of non-differentiability. So I'll make sure I do that before we are done today. I can tell that some of you are fuzzy on the logic here. Those true-false questions that I put out are really good ways to become unfuzzy on those issues, because those questions ask you some things to help keep your head straight on the theorems. And the key is to know the if and the then part of the theorems. So if f of c is a local max, then what do I know? Critical point. Either f prime of c is 0 or it does not exist. Does it go the other way? No. If f of c is an absolute max, what do I know? X equals c is critical point or an infinite. And that's it. Okay. The third use that we had for derivatives was to find instantaneous rates of change. And the key with this is a language game. In particular, we found instantaneous rates of change with motion along a line. This was one of the big ways in which we use derivatives. So if I have a position S of t, then the derivative of that position, ds dt, is the instantaneous rate of change of the position, also known as the velocity. And because this is the instantaneous rate of change, the velocity tells me some things about the motion of the particle. If my velocity is positive, that tells me that my particle is moving how? To the right or up, right? And if my velocity is negative, then my particle is moving left or down. And the reason for that is really simple. It is the instantaneous rate at which my position is changing. So, if my velocity is positive, my position is increasing through that time. You see it? And if my velocity is negative, my position is decreasing through that time. What if my velocity is 0? What do I call that? We could also apply the logic of derivatives to the velocity. And the derivative of the velocity is called the acceleration. And the acceleration is a little harder to visualize. It isn't how fast you are going, it is how quickly your velocity is changing. So that if my acceleration is positive, my velocity must be increasing. And if my acceleration is negative, the velocity must be decreasing through that time. But not necessarily the speed. What is the difference between speed and velocity? Speed is
Just the magnitude.
which is, so let's say that it matters. Absolute value, that's right. So speed is the absolute value of that velocity. And is my speed always increasing if my velocity is increasing? No. Under what circumstances? Well, here's one. Do we all agree that right at this time C, my velocity is increasing? Yes. How do I know? Because its derivative is positive. But is my speed increasing? No. And you can see that by taking a look at the absolute value of the speed. and see that my speed is actually going down while my velocity is going up, because my velocity is becoming less negative. It's heading towards zero. So how do I tell if my speed is increasing? I look at the signs of both together. If my velocity and acceleration have the same sign, speeding up. And if they have opposite signs, slowing down. That's right. Acceleration and velocity have the same signs. The object is speeding up. The object is slowing down. Velocity, acceleration have opposite signs. Now, motion was the biggest way in which we use derivatives, but it is not the only way that we could use derivatives. We can more generally use derivatives to refer to any instantaneous rate of change. I know I wrote this before, I'll write it again. Derivatives are instantaneous rates of change. So, for example, let's suppose that I've got a circular vat, and in the it's maybe let's be more specific. Let's say it's a water cooler, and it has a little spigot at the bottom, and my water cooler is filled up with water, like this, and somebody comes along and turns on the spigot, so now water starts coming in. Okay? And through whatever means, we model the height of the water at a given time as, how about, let's make it 5 over the square root of t plus 10. It's actually a realistic model. And so now we ask the question, what is h prime of 2, and what does this mean? Usually these questions will have units with them, so an appropriate unit for height might be yeah, let's go with feet will work. And an appropriate time for t might be in seconds. This thing is reading us fast. It's got a big speed. Okay. And so now we ask, what is h prime of 2? What am I, as soon as I see this, what are my possible options for finding h prime of 2? Derivative rules? Calculator, right. And so it would depend on what I have available. Let's say I have calculator available. Find h prime of 2. Go. What'd you get for h prime of 2?
Negative 0.0601.
Yes. 4 zeros. Negative
0.0601.
And what else do I need to write with this? Well, how many decimal places does my answer need? Everybody loudly, how many decimal places does my answer need? 4, right? Do I need to show any other work? No. I do need a label, h prime of 2, I need to answer the question. And I also need units, and what are the appropriate units here? And how do you know it's feet per second?
Units.
It's like a velocity, that's right. It's the units of h divided by the units of t, because the other way that I could write this is dh over dt. And so it has to have units of h divided by units of t. Okay? Now the second question is, what does this number mean? What is the meaning of h prime of 2 equals negative 0.0601 feet per second? And to answer that question, our answer should really have three components. First of all, it should explain the meaning in terms of the words increasing or decreasing. Is my water height increasing or decreasing? Does that make physical sense given that I've opened up a spigot? Yes.
Yes.
So this means that this is the first component of my answer. Water is decreasing at a rate of 0.601 feet per second. So this is the first magic word that my answer needs to have in there. It is decreasing. And I know it's decreasing because the derivative is negative. Second, I'm going to provide the actual rate with the units. Notice that I do not put a negative sign there. The negative sign is taken care of right there. So if I were to put a second negative sign, at best it would be redundant, at worst it would be confusing. Is that supposed to be double negative? It's really increasing. Don't do that. It's decreasing at a rate of 0.0601 feet per second. And then finally, I need to be specific, be specific. Is it always decreasing at this rate? No, it's only decreasing at this rate when? At t equals 2. And so this is how we generally use the derivative as a rate of change. We interpret as a rate at which we are increasing or a rate at which we are decreasing. And those are the uses of our derivatives. Yes, sir.
I was looking at this midterm review budget, and one of the questions seems a little bit difficult to not use a calculator.
Let me see.
I'm trying to do in my head that
I agree. Yeah.
I've got up to L and 3/2 divided by 4 square root. I don't know what that is.
Yeah. Is that packet 1 or 2?
That's packet 2, question 3.
I didn't do quite as good a job as I need to vetting that question. The question number 3 on the midterm review 2, you would have to have a calculator for. Yeah.
And number 6.
You think number 6 also?
I was doing it last night
Yeah.
and I got there. And I was like, I don't know how to solve it.
No.
Number 6.
And then the
Is
answer
equal to 3x to the power of 2x.
Okay.
it said like graph the derivative and like find the intersection, and I was like,
Can't do that.
Right.
So please be aware.
Is equal to fx.
Sorry, guys. Hold on. Please be aware that you will need a calculator for those of you.
What is the tangent line?
Last thing that I want to say before this, the one thing that we didn't do is to practice graphing a rational function. So I'll put out a short video that just reminds you of all the things that you need to know about graphing a rational function.